So what we're going to be looking at here, guys, is some stuff that's going to be useful when we're doing our properties of compounds lab, but also relates to a lot of things that are going to go on in the chemistry unit. Okay, obviously the first part has to do with solubility. That's going to be one of the tests that we're going to do, okay, in our properties of compounds lab. So we'll talk about some terminology related to solubility, okay, what solubility is, that kind of stuff. And then we're going to talk about a bunch of the special things that water does. Okay. Water is what we call a polar molecule. Okay? Polar molecules behave in a very specific, sometimes odd way compared to other types of molecules. Okay? So we're going to talk about what a polar molecule is, and you can see that that's underlined up here. Okay? Being able to tell me what it means to be a polar molecule is an important thing that you've got to be able to do. I cannot remember a unit exam where I did not ask for that to be explained. Okay, so being able to explain to me what a polar molecule is one of those things you must be able to do by the end of this unit. Okay, and then obviously be able to explain also some of the behaviors that polar molecules will show. Okay, the polar nature of water is the reason a lot of things work the way they do in the natural world. Okay, okay. Solubility. What's solubility? If something is soluble, what can it do? It can dissolve, okay? Right? Most of the time, we consider solubility related to how well does it dissolve in water, but it doesn't always mean that. Okay? Some things aren't soluble in water, but they're soluble in other things. Like, for example, if you've been like staining or painting your deck, okay, or your fence or something like that, okay, that stuff doesn't normally come off of your hands very well, okay, with just soap and water. So you use instead, what else can you use? Well, bleach won't take it off either. Rubbing alcohol can take it off a little bit, okay, but usually you use paint thinner, okay, Varsol, okay, even if you're really brave, don't do this, gasoline, okay, gasoline will take it off, because those are not polar molecules where water is. Okay? So sometimes if you have something that is a non-polar molecule, it isn't soluble in a polar substance. Okay? It's soluble in other non-polar things like gasoline, paint thinner, okay? Things like that. The reason I say don't wash your hands with gasoline is because if there's any source of ignition nearby, that goes badly. Okay? Well, then you can go and a lot of soap and water will generally get gasoline off of your hands, generally. Not always, but generally, yes. It's very difficult in chemistry to have a hard and fast rule about anything because there's always an exception. Water tends to be the exception to every rule. Okay? All right. So when we're talking about solubility, okay? Solubility is the degree to which something will dissolve in something else. Okay? Not always water, but often water. Okay? The degree to which something will dissolve in something else. Okay? So if something dissolves easily, we say it's highly soluble. If it doesn't dissolve or dissolves very poorly, then we say it has a very low solubility or it is insoluble, which means it doesn't dissolve at all. Right? And there are some things that are like that. Okay? So, substance is insoluble if it will not dissolve in another substance. If a substance remains insoluble and in a solid form, or is produced as a result of mixing two things, a solid is produced. We call that solid a precipitate. All right? And you can see that that is circled. Precipitate is an important term. Right? We call it a precipitate because usually when it's formed, it will then fall out of the solution and collect at the bottom, kind of like snow falls out of the sky or rain falls out of the sky. We call those things precipitation because they fall out of something else. Okay, so it's a precipitate if it falls out of the solution, collects on the bottom. Okay, sometimes a precipitate will float, but it comes out of the solution. Okay, in the same way that precipitation does. Okay. Everybody follow me there? Okay, so this is something that would be soluble. We don't see any solid materials or divisions between the fluids or things like that. Whereas in this case, we do have something that is insoluble here, and it's probably starting to fall down towards the bottom of the test tube. That stuff wouldn't dissolve. That would be a precipitate. Okay. Is it possible for a liquid to be soluble in another liquid? Yes, it is. We often think that when something's soluble, it's a solid dissolving in a liquid, okay? But it can be a liquid dissolving in another liquid, right? That's what you were doing with paint, okay? You want to make paint thinner, you add paint thinner to it, okay? That makes the paint more soluble, makes it a little bit thinner, okay? Dilutes it a little bit, right? If you're adding like, let's say, like broth to a stew or something like that, you've got two different liquids. You're pouring them in there, they dissolve, okay? It's a liquid into a liquid, but they're still becoming one visible part together, okay? If you're, not that you guys will have done this, but if you mix, alcohol with some other thing, okay, they will dissolve. Alcohol is soluble in water, okay? So when you mix them together, it doesn't float to the top. Unless you mix it with the wrong stuff, then it does float to the top, and that first sip is real awful, okay? Yeah, you gotta be mindful of that. Eggnog is one of those, okay? Okay, yeah, anything that's kind of milky like that, generally then that's not going to be as soluble, and you'll get a liquid that floats on top of another liquid. Oil and water, prime example, okay? You pour oil in liquid, okay, and you get the water at the bottom, the oil on the top. They're not soluble with each other, okay? It's not a precipitate per se, it's not a solid, but they sit on the top. They're not going to mix with each other. And if you shake it up, okay, you give it a couple minutes, the oil's going to go right back to the top again, okay? Now, if you put a drop of soap in there and then shake it, what'll happen? Then it'll mix, okay? You've changed the solution, okay? Soap essentially breaks up or emulsifies oils and makes them more soluble in water. That's why we use it to clean dishes and pans and things like that. All right, terminology. A solution is any mixture that contains a solute dissolved in a solvent, okay? The solute is the thing getting dissolved. The solvent is the thing doing the dissolving, all right? Water is often known as the universal solvent because it dissolves most things. Okay? A true solution is also known as a homogeneous mixture, okay, or homogeneous mixture, however you want to say it. Either way is equally correct, okay? A homogeneous mixture, right? The prefix homo means what? One, yeah, okay, or the same, okay? Either one, okay, is a definition of that prefix. So if we have a homogeneous mixture, it means it has only one visible part. It may have more than one part in it, but there's only one visible part, okay, and it is all one, okay? So that's why if you buy milk, okay, milk is homogenized. That way the cream doesn't rise to the top and the water separate at the bottom, because if you take it right out of the cow and leave it, okay, that's what happens. The cream rises to the top, the water goes to the bottom, okay, and then you have to re-stir it and whatever, okay? So we typically go through the process of pasteurization with milk products in order to keep that from happening and keep them homogenized. Peanut butter is another one, okay? If you buy like all natural peanut butter, okay, it will not be homogenized. And as a result, you will have to stir it every time you use it because the peanut oil will go to the top and all the other stuff will go to the bottom, okay? Not homogenized. That's a mechanical mixture, okay? You're forcing it together. So a heterogeneous mixture, okay, otherwise known as the mechanical mixture, has two or more visible parts, okay? There is no way to suspend or dissolve one of them in the other, okay? So the one on the left here, this would be a true solution, a homogeneous mixture, okay? This would be a heterogeneous mixture, okay? Hetero meaning two or more than one, okay? And they are visibly separate here, okay? So a mechanical or heterogeneous mixture. So oil and water would be a heterogeneous mixture, okay? You go to Subway, okay, and they got the shaker that's got salt and pepper in it. For whatever reason, okay, they don't have them separate, okay? That's a mechanical mixture. Huh? Yeah, that is separate. Yeah, that's what I said. Okay. For some reason, they put them in the same shaker, right? But that's a mechanical mixture. Okay. Those kinds of things. Everyone follow me there? Salad dressing. Salad dressing is a mechanical mixture, right? You got the oil, you got the vinegar, you got whatever else is in there, chunky stuff. Okay. If you like your salad dressing that way, okay, that's a mechanical mixture. Everybody follow me there? All right. Think about a mechanical mixture or a solution. The parts can be separated. Okay? It's not a chemical reaction. I can separate the two parts by a physical means. All right? If I dissolve salt in water, how can I separate the two later? Evaporate the water. I can use the boiling point of water to separate it from the salt, because the salt won't boil. Okay? The water will leave. Okay? The salt will be left behind. Right? That's what happens if you boil away all the water in a pan at home. Don't do that. Okay? It's really nasty because all the dissolved solids in the water stay and they char onto the bottom of the pan, and it's almost impossible to clean. Okay? Right? But you can separate them by a physical means. If I mixed a whole bunch of iron filings into sand, okay, how would I separate them? With a magnet. Right? I could just stick a bar magnet in the mixture, stir it around, and pretty soon I have all the iron filings stuck to the magnet. Okay? And I'd have separated them by a physical property. Iron filings are magnetic. Okay, or attracted to a magnet. Sand is not. Right? If I had sand and sugar in the same container, how would I separate them? No, I don't think so. It wouldn't be very good glass because they might still, right? The sugar would melt as well, okay? And they're around the same melting point. You probably could, yeah, add water. Okay? The sand won't dissolve, right? The sugar will. Give it a shake and then filter it off. Okay? All the sugar water will go through the sieve and all the salt will be left behind. Again, it's a physical thing, solubility of the sugar. Okay? If I had rocks in sand, I could separate them just by their physical size. Okay? I could just have a strainer that allowed the sand to get through, but not the rocks. Okay? Things like that. They can always be separated by some physical means. It's not a chemical change to dissolve something in something else. Okay? Okay, terminology again here. The solute, okay? The solute is the substance that's getting dissolved. All right, if I put salt in water, salt is the solute, water is the solvent. Okay, so similarly, solvents are any substances that will dissolve another substance. Okay, that's why we typically refer to cleaners as solvents. Okay, like CLR is a solvent. Okay, Mr. Clean is a solvent. Okay, Lysol is a solvent because they dissolve things that water by itself has difficulty dissolving. Okay, so they help those things become solutions that can then allow them to be removed from the insides of toilet bowls or bathtubs or whatever. Okay, and then they can go down the drain. Okay. Okay. What kind of things might affect how much of something you could get to dissolve, or how much, or the solubility of something? Are there ways you could get more stuff to dissolve? Temperature is a big one. Okay, temperature affects solubility. The hotter something is, the more stuff will generally dissolve in it. That is, the hotter the solvent is, okay, the more solute will dissolve. Okay, I know when I used to make Kool-Aid all the time, I would actually make Kool-Aid with warm water. Okay, because then I could get more sugar to dissolve in it, because I figured Kool-Aid was perfect if there was a thin film of sugar at the bottom of the pitcher. Okay, because I can get it to dissolve the first time, but as soon as I throw it in the fridge, the solubility of the sugar is reduced, and some of it precipitates out, collects on the bottom, which means I now have a saturated solution of Kool-Aid. Okay, well, not quite super saturated. Okay, it was super saturated when I had it hot because it had more in it. Okay, all right, what else? Agitation, okay? Stirring stuff. I mean, that's just something we do instinctively. Oh, I put something there, I better stir it, okay? It makes it go away faster, okay? The movement of the particles of the solvent will help more stuff to dissolve, okay? All right, precipitates, any solid that is produced in a reaction and will not dissolve in the solution. Okay, now I'm going to show you a quick little video clip of what that looks like. Okay, when a precipitate is produced, we'll actually do that in a few weeks. Okay, when we do our chemical reactions lab, we'll have a couple of reactions that will produce precipitates. You'll mix two clear things together and suddenly you'll have a solid. It's not going to turn into like one big solid mass, but a solid will form inside. All right, so I'll show you what that looks like here. Okay, this is what happens when you replace natural ingredients with artificial ones. Okay. The original Twinkie, was cake. Okay? It was cake with filling inside, right? And the cake was made of things like eggs and flour and milk. And the filling was made from things like butter or cream and sugar. Okay? The problem with that is those kinds of Twinkies go bad. So they don't last on the shelf very long. That's not good for business. So the Twinkie was altered to include more artificial ingredients that don't go bad, like ever. Like the shelf life of a Twinkie is like longer than we'll live. Okay? Not really, but okay, it's a long time. Okay? Because it basically no longer contains any natural ingredients, right? The eggs have been replaced by some sort of protein powdery kind of thing. Okay, the flour is still flour. Okay, the sugars, they're still there. Okay, they want to keep this thing for a long time, so they add preservatives to it. Okay, preservatives basically inhibit the growth of bacteria and fungus on the Twinkie. Okay, the problem is if it's bad for bacteria and fungus, it probably isn't all that good for us. Right? They add some stuff in here that's part of mortician's fluid. What does a mortician do? Yeah, it's the stuff they put in dead bodies before the funeral so that they don't get smelly by the funeral. Yeah, it's not like, I'm not saying they did it. That stuff is exactly in there, but some of the stuff that's in mortician's fluid ended up in Twinkies, okay? Because it makes them last on the shelf a little longer, or a lot longer as the case may be. Here's the thing. The original Twinkie, being made of eggs and milk and butter, those things were not soluble in water. So if you put the original Twinkie in water, it would just suck up the water like a sponge. Okay? The modern Twinkie dissolves in water. It is actually water soluble. You leave it in water long enough and you get this nasty looking pool of Twinkie. Okay? So if you ever got your jaw wired shut, you could still eat Twinkies. You could just put them in water and then have a turkey or a Twinkie shake. Twinkie shake. Okay? Yeah. Right? It'd be kind of nasty, I don't know, but hey, if you really like Twinkies that much, it would be okay. Here's the other problem though, guys. The natural original Twinkie being made with eggs had this nice golden color because of the egg yolks. When they replaced the eggs with the protein stuff, they ended up having a Twinkie that looked like it was made out of drywall. Gray. Nobody wants to eat a gray Twinkie, okay? So what do they add to it? Yellow dye number 5. Known carcinogen, banned in many countries. Okay? Part of Twinkies, give them that nice no egg color. Okay? Right? Yeah, yellow dye number 5 is actually very bad for you. But it's one of the ingredients in Twinkies. Okay? They're actually looking at a way to replace it because it has been found that yellow dye number 5 is a carcinogen. That means it causes cancer. It's very bad for you. Okay? I don't know why it's called yellow dye number 5. Maybe it was the 5th yellow dye. I don't know. Maybe there is. Yeah. Okay. Well, you can look it up later. We got to get through this, and we're running out of time. Okay. So, like we said, some things are soluble, some things aren't, some things should be, some things shouldn't. Okay. Twinkie now made of things that are all water soluble. Okay. All right. On the back of your periodic table, take out your periodic table, flip it over. On the back of your periodic table, you see something that looks like this. Okay. Not exactly like this one, but sort of like this one. Okay. This is a solubility chart. It allows you to figure out whether a substance is soluble in water or not. Okay. Here's how it works. Along the top, okay, basically are your negatively charged ions. Okay, your anions. Okay, and then along the bottom, okay, in the bottom 2 rows are basically the metals that they could be attached to, or polyatomic ions that these things could be attached to. Everybody follow me there? If something is in the first row, it is very soluble. If it is in the second row, it is either insoluble or has a very low solubility. Okay, so here's how we use this. If I give you a compound, let's say I give you this, and I ask you, is that material solid or soluble in water or not? Okay, here's what you do. You look at the non-metal, and you go, okay, sulfur. Here's sulfur right here on my solubility chart. And it says that sulfur is soluble when it is with hydrogen, sodium, That's what it's with here. Potassium and these other things. Okay, so is this substance soluble or not? Yes, that substance is soluble. Whereas if I gave you, let's say, this stuff, okay, I go across till I find sulfate, okay, the negatively charged part of that ionic compound, soluble with most things. That's a really bad thing to write in there because you don't want to just assume that what you have is part of most. Then go down and check, okay, nope, calcium is down here. In fact, it's the first thing listed. This stuff is not soluble in water. Is that pretty straightforward? Okay, how to use that? Okay, it's pretty easy. What I'm going to do on an exam, okay, or a quiz is when we get into chemical reactions, is they'll say, you know, find out what the products of this reaction are, and then tell me which, if any, are soluble. Okay, so you might say they're all soluble. They might say only this one is soluble. Neither one is soluble. Okay, that's what you'll be asked to do kind of with this stuff here. Okay, so I want you guys to tell me, write those down. Use your solubility chart to tell me whether they are soluble or not. Okay, 1 through 8 there. I'll help some other people here. So we got, for number 2, we got sodium with sulfate. Okay, so when we look up sulfate, it says soluble with most things, and then there's a list of things it's not soluble with. Sodium is not on that list, so that one's soluble. Okay, ammonium nitrate. Okay, ammonium's in the first one there, and it says it's soluble with everything. It says all and none below. Okay, so that one's definitely soluble. For number 4, chlorine and silver. Okay, chlorine's in the middle there, soluble with most things, but silver's the first thing listed as not soluble. Okay, for number 5, we got iodine and lead. Okay, so iodine's in that same group with chlorine, and lead is listed in the non-soluble row, so that's an NS. Okay, H2S, so sulfur, and if you see here it says group 1A on your chart. Group 1A is the first group of metals on the periodic table. Okay, group 2A is the second group of metals on the periodic table. Okay, so that's what they're talking about. Hydrogen is in group 1A, so that's soluble. All right, phosphate and potassium, says phosphate soluble with group 1A, and that's where potassium is, so that one's soluble. Okay, and for number 8 with mercury and chlorine, okay, mercury is listed in the non-soluble row with chlorine, so that one is not soluble.